right. So today I'm going to discuss different topic than yesterday. This is more related to building prediction intervals for a time to event outcome, an outcome that's subject to right-censoring. And the idea is trying to do so while being well-calibrated in the sense that I'm going to define, and allowing for the use of flexible machine learning methods to build the learner for the prediction. And so, just by way of introduction, if you're not familiar with survival analysis, it stands a little bit apart from standard regression and statistical analysis in the sense that right censoring is quite prominent with every time data. And that is that individuals are followed over time, and we're interested in time from start of follow-up till the occurrence of a given event. And however, patients or participants may be right censored, which means that an individual's event time, the exact event time, remains unobserved. And that can happen if the individual either drops out of the study or if the study ends before he experienced the event. And so this is a very common occurrence in clinical trials where survival or time to progression or either time to event outcome might be of interest. So if you think, for instance, about the recent COVID-19 vaccine by Moderna and Pfizer and other companies, the trials were actually powered to detect a reduction in the risk for time to infection, right? The risk for time to an individual getting infected with and showing symptoms of COVID. And so this is a very common outcome. And by the time the study was stopped, after 3 or 4 months, the vast majority of individuals hadn't experienced the event. Nevertheless, they were able to detect a remarkable difference in the survival rate among the survival in the general sense of time to infection among those who received vaccine versus those who didn't. So the most standard, the most common randomized trials are actually usually with respect to a time to event outcome. Just to give you a sense that this is actually a very common occurrence in randomized experiments. So classical survival analysis methods abound, and several methods have been developed over the years to deal with right censoring. I mentioned a couple here that you may have heard of or used in practice. The Kaplan-Meier is probably one of the most cited papers in statistical literature. That is a non-parametric estimator of the survival curve, appropriately accounting for right censoring. And the Cox proportional hazards model is also sort of a very well-established method in statistical inference due to David Cox, who passed away actually somewhat recently. And the Cox proportional hazards model is sort of the basis for powering randomized trials. So the FDA would actually expect you, if you're doing a randomized trial, you're designing a trial where the failure time outcome is the endpoint of interest, they expect you to power it towards proportional hazards. And this remains a kind of a standard. Whether or not you believe they hold, that's something different. I'm going to get into that. That the assumption that the hazards are proportional between the two arms hold. I'll get into that a little bit later. So anyway, this is just to give you a sense that there are tools that have been well developed. I give a few citations here. There are millions of citations that would be relevant to this topic. Today, I'm actually going to focus on uncertainty quantification associated with point predictions, because this remains a difficult issue, particularly when we decide to move away from standard regression modeling and to use machine learning techniques to build prediction algorithms. Prediction intervals, which with a specified marginal coverage guarantee, offer a promising solution to overcome some of these limitations as an alternative to conditional inference on point prediction. So I'm going to focus on these idea of building a prediction interval for the time to event outcome of a given person, potentially subject to censoring. We're going to borrow some ideas from conformal inference, and there are two key ideas from conformal inference that we're going to borrow. One is to make your target of calibration the marginal coverage, and I'll explain what that means, as opposed to conditional coverage. And I'll get into that in a second. So this is an idea that I think has been championed by the proponents of conformal prediction, which I think is a fair trade-off between the impossibility for conditional coverage in a specific sense of conditional covariates versus marginal coverage and the added robustness that provides. The second aspect of conformal prediction we'll leverage today is this idea that you can be agnostic as to the prediction rules. So if I whether use random forest or use a regression model to build your prediction rule, the coverage guarantee will not depend on the validity of that learner. So this is a very powerful idea that the better the learner, the tighter your predictions are going to be, the more robust they're going to be, the more efficient they're going to be. If your can I get rid of? Thank you. If your models are to be specified, the coverage guarantee will still hold. However, the prediction interval will be a little more conservative. So I think these two powerful ideas are worth considering, particularly in these challenging settings. So I'm going to describe today two methods one can use to do this in the context of censoring. Two methods to construct well-calibrated, lower predictive bounds for time to event outcomes subject to right censoring, while guaranteeing coverage. There are two key ideas here that build upon modern semi-parametric efficiency theory. I won't describe that theory in detail, but I will try to give some intuition as to why it's useful in this context. The first one is inverse-probability of censoring weighting, IPCW, and the second one is augmented IPCW. And this goes back to ideas from the early 90s by Robbins and Rudnitsky and colleagues, whereby inverse probability of censoring weights is used to deal with potential selection bias due to censoring. For both methods, what we'll demonstrate is that actually we believe this is the best one can do is finite sample coverage guarantee is not attainable in this context because of the censoring mechanism. Okay, and so the most one can hope for is to establish asymptotic coverage guarantee in this context, and we'll show that in fact AIPCW in that sense has some advantages over inverse probability of censoring weighting, in the sense that AIPCW will provide a coverage error term which is of second order, that is a smaller order bias than IPCW. This is quite abstract as an introduction. We'll work to make these ideas very concrete in the next few slides. Motivating example for why you might be interested in doing this are really twofold. One is you might be interested in identifying the primary predictors of a unit's time to event risk. You might be interested to generate individual event time predictions with reliable uncertainty quantification. Examples include disease progression, infectious diseases, time to infection with HIV or something like the flu or COVID, or, and of course, this is important, as I mentioned earlier, in randomized clinical trials. The example I'm going to, hopefully I have enough time to get into later on, is a setting where there was a drug called methotrexate, which is a cancer therapy that was being considered for repurposing for individuals suffering from rheumatoid arthritis as a way of managing the tenderness of arthritis. And so in this study, it was actually shown that this medication worked quite well. It could be repurposed. Not only could be used for cancer, but also could be used to deal with patients who have chronic RA patients, arthritis patients. In that context, we'll see whether, in addition to this therapy that patients were being prescribed, whether baseline characteristic could also predict time to death So mortality will be the outcome. And the idea is essentially that it's a physician sees a patient coming in, and they interview the patients, measure the biomarkers, take the blood, measure all relevant biomarkers, include characteristics such as age, gender, that tend to be correlated with things that are causal for mortality in this population. Whether they could actually have an idea of whether this patient is at high risk or low risk. Okay, and so the goal is twofold. One is, can we find a lower bound on the time to infection or time to death in that example for a new patient that will show up? You need a predictive algorithm. Some of you may be younger now, but when you reach a certain age and you go to see the doctor, they will sometimes run a CVD risk. So they'll ask you a bunch of questions: how much do you drink, how much do you smoke, and then you'll say, well, okay, it looks like you have a probability blah of dying from CVD in the next 10 years or something, or serious case. So those algorithms, those scores, are actually coming from a model. Okay, and so the idea is that this is actually something that's being used in practice, and the better those models are calibrated, the less uncertainty there is in this messaging that doctors are giving out. The more uncertainty there is in those messaging, the less the patient can actually rely upon such advice from their physician. And so there's a direct correlation between our ability to construct reliable, well-calibrated predictions and the health of patients. Okay? So this is not just math for the sake of math. It translates into actual allowing physicians to do a better job on the ground. All right, so that's enough backstory. Let's jump right into what this means statistically. So I'm going to use the following notation. X will be a vector of covariates that will be used to build a prediction rule. T is survival time of interest, and C is time to censoring. Okay, so survival time is right censors in the sense that only T or C is observed, whichever comes first. That's what it means to be censored. Is that there's an online censoring time that masks your ability to observe T if it occurs before T. Okay, so the observed time to event is actually Y, which is the minimum time from start to follow-up between time you experience the event or time you were censored. Okay, so note something here. This is a very interesting form of missing data, because even if you're censored and I observe your event time, there is information about your event time in the censoring time, because I know that if you're censored before you experience the event time, well, your event time is at least as large. Okay, and so you want to be able to, you want to avoid just throwing away data for people who are censored, because there is actually information in those censored individuals. And so the one question is, how do we recover that information reliably? All right, and so the observed data are X, the covariates are observed on everyone. We're using R to index the individual, the random sample. Y, which is the minimum between T and C, whichever comes first. And then delta, which is an indicator that tells you whether or not you observe T for that person. So think of a data set. One row with the identifying the ID number for the patient. So that's row I, patient 1, patient 2, so on. And then you have time to event, you have Y. And then you have an indicator for that patient whether Y is actually T or C. Okay, so it's assumed that we observe all of those factors. In the rheumatoid arthritis example that I mentioned earlier, that we'll come back to later, that's in fact the case. We know whether or not a patient dies up to the time where they are censored. Okay? If they die before they're censored, well, we know that they died. If they're censored before they die, that means that they dropped out of our study. And we have no idea when they potentially died, if at all, during the course of the study, after they drop out, rather. But we know when they drop out. Okay? So that's the observed data. The full data refers to what we wish we had observed had we been able to prevent censoring. And that's, of course, X and T. So if I observed X and T, then I could just rely upon standard conformal prediction or any other prediction algorithm that's available. So the issue here is how do we deal with this censoring mechanism? Okay, and to recognize that the censoring mechanism can actually introduce some bias if you're not careful, but also that there's information in the censoring mechanism. You want to pull that information carefully, and so we're going to require some careful consideration in trying to do so. All right, so here's our goal. The goal is to construct lower predictive bounds, which I'll sometimes refer to as LPB, for the survival time t by leveraging covariates X while guaranteeing coverage. What that means is that we're going to construct some rules, L hat, which are going to be rules that depends on data, X. And it's going to be a function of the covariates estimated from the observed data. And then let alpha be a fixed level that you as a user will want to calibrate towards. So like a type 1 error type level. And here's a definition of what we mean by this rule, L hat, this predictive rule, to being marginally calibrated LPB for T at level alpha. That is, if for any new data point from your underlying population, so doctor sees a new patient, they observe X and T plus 1 for that patient, they ask them, and they want to predict Tn plus 1. Well, this is a valid, marginally well-calibrated LPB at level alpha if the probability that the patient, this is the true probability that the patient's failure time is greater or equal to the lower bound that you provide them, is that probability is bounded away from 1 minus alpha. So it's greater or equal to 1 minus alpha. So think of alpha as like 10%. So this would be 90% confidence prediction interval for the patient's lower bound. So this would be something that you will report to the patients that we are certain with probability 90% probability that you would experience the event at a time past L hat. That's a lower bound. You can likewise construct an upper bound, and you can provide an interval. Okay? And the idea of well-calibration is that we have this guarantee that there is, for every single patient, we can provide a guarantee that this lower bound will cover the patient's survival time with probability 1 minus alpha. Okay, let me pause here to see if there are any questions. This is just a definition. Yes.
For the xn plus 1, is it fixed or is
Very good. This is the marginal probability with respect to the joint distribution Tn plus 1, Xn plus 1. Everything is with respect to the joint distribution of X and T, therefore random mix. Okay, this is really important. Everything I'm going to say today, in fact, everything in conformal prediction is with respect to the joint.
And on the previous slide, C is fixed or random, or does it matter? The censoring time?
No, it's random. Yeah, so the censoring time is random because imagine this study. So I'll come back to this in a second because there are some settings where it's fixed. So in the study that I was describing, patients, this is a cohort study. So you invite patients to join your study. And every month they come in for an interview, you check their blood, they come in for a health screening as well. And then, month after month. And at some point they may drop out of your study. That means they decide no longer to show up. That's the censoring time. You have no control over that. You would like them to keep showing up until the end of the study. But unfortunately, some people move or decide they're done with the study, they feel good, or decide they don't feel well enough, they don't want to engage in this, taking too much time. For whatever reason, they drop out. And this happens. Now, there is also the kind of censoring called administrative censoring. That is, I plan a cohort study that ends after 1 year. For anyone who hasn't experienced the event, by that end of that study, they have a fixed censoring time, which is 1 year. Because I know up to the end of the study, they haven't experienced the event. Okay? So that's known as administrative censoring. For the purpose of today, administrative censoring is very easy to deal with. And I'll come back to this in the slide because a lot of the previous literature for this problem have mainly dealt with administrative censoring. Okay? We are going to consider a more general form of censoring. And in fact, we'll allow censoring to be correlated with the failure time up to the covariates. Okay? And well, that's why we're going to need to address censoring, because the reason a person might drop out of study might be related to actually them not feeling so well. Okay? And then, so you want to account for that. All right, very good questions. So we keep going. All right, so I'm going to introduce now these ideas of probably approximately correct, lower prediction bounds. And so we often have one observed data set, so we require coverage condition on the observed data. And therefore, this definition is going to be useful. L hat is an alpha and epsilon. So now we have two parameters that we want to set to calibrate. So L hat is an alpha epsilon pack, probably approximately correct lower prediction bound for T. If for any new data point, xn plus 1 and tn plus 1 coming from the underlying joint distribution, we have the following. So the main difference here is this inner probability was the definition of the lower prediction bound, well calibrated. We're now conditioning on the data that was used to construct L hat. And we want that probability to be controlled at 1 minus alpha. But this is now a random statement because we're conditioning on the data that was used. And therefore, we want that to happen with high probability, controlled by 1 minus epsilon. Okay. So the probably approximately correct here comes from, this bracketing. The fact that you first conditional on the data that was used to train the algorithm, and then you marginalize over all realization of that probability. And you want this event to occur with high probability. So calibration here is twofold with respect to alpha and epsilon. Okay. Now, this may not be achievable actually in many settings, in which case one would have to revert to an asymptotic notion of alpha epsilon pack LPV. And it's essentially the same consideration with the exception that we recognize that we may not be able to attain 1 minus alpha exactly, and you allow for some slack, a slack of little OP1. Where does this come up? This is going to come up, for instance, when we want to account for censoring. When we want to account for censoring, we have to estimate the censoring mechanism because we do not know it. That will introduce uncertainty, and that will introduce this little OP1. Okay. How you introduce your correction for censoring really matters. So the order in which this converges to 1 will depend on how you actually incorporate your censoring mechanism. Okay, and so here's the hierarchy of calibrations that one can potentially attain. The one that we'll demonstrate is actually feasible is this one. And we have some impossibility results with respect to the other ones, if in fact there is censoring that's informative. Okay, impossibility results in the sense that if there's any L hat that attains this definition, that L hat will necessarily be the whole line. So it's not an informative prediction overall. All right. How do we use these definitions? Well, first I want to describe what an oracle would do. So the construction of prediction bound is actually quite simple. Why is that? Well, if you look at the statement, let me just go back to the initial statement. If Tn plus 1 were actually, so Tn plus 1 is a random variable, therefore this is actually the survival curve of Tn plus 1 at L hat, if I were able to condition on Xn plus 1. And I want that survival curve to be greater or equal to 1 minus alpha. How can I attain that? Well, just pick L hat to be the 1 minus alpha quantile of the distribution of T given X. That's what an oracle would do. If I had the law, then prediction interval is just adjusting the quantile of the outcome, and I'm done. Why do I need to do all that? Well, I need to do all of this because it turns out if X is high dimensional or has continuous element, estimating the law of T given X is infeasible without any additional assumption at any reasonable rate. Does that make sense? Because estimating the distribution of T given X is estimating a distribution that may depend on covariates in a fashion that it can be very smooth or very non-smooth. And you cannot guarantee any arbitrary rate without placing some restriction on how smooth that distribution is. All right. So I'm gonna now go back and then say, okay, well, let's first articulate what an oracle would do. If they, in fact, could do what I just described earlier, that is effectively estimate the distribution of t given x. So what would they do? So I'm gonna need two objects. We define S star of t given x as the survival curve for t, divided by little t given x. So that is the true underlying survival curve for the outcome t. We likewise define C given S of C given X, and the stars will always indicate the underlying true law that generate the data. And so denote that S of C given X star to be the survival curve for censoring, given the covariates. Okay? And so, as I mentioned earlier, the oracle lower prediction bound would actually be the alpha conditional quantile of t given x. That is L hat of x, defined as the alpha's conditional quantile of the distribution of t given x, which is denoted this way. We'll call it Q, and that's the definition, which is the smallest value of t such that the survival curve is less or equal to 1 minus alpha. Survival curves decrease. They're decreasing functions, right? Because at the start of follow-up, everyone is survived. And as you continue to study, the survival curve goes to 0 eventually. Because eventually at some point in time, everyone is there. Okay, so it goes from 1 to 0. And if I want the alpha's quantile, I just look for the first time where the survival curve crosses 1 minus alpha. But this is a conditional survival curve, given covariates. This is what an oracle would use. If you had access to this, the talk would be done right now. We could all walk towards lunch, right? And the whole point of this talk is that you do not have access to Q, okay? And so we have to try to deal with that. So I mentioned earlier that there is some prior work that has considered this problem. Emmanuel Candace, who is a well-known statistician and well-known academic in both statistics and machine learning, recently, and Gui and colleagues recently considered the similar problem. However, this is going back to the question about whether censoring time is fixed. They only consider a case where one fully observed the censoring time. So if you think about the example that I mentioned earlier of administrative censoring, if that were the only source of censoring, then you know exactly what the time to censoring is for both individuals who were censored and didn't experience the event before they were censored, but also individuals who were censored, who experienced the event before being censored. And so they only considered this is known as type 1 censoring, where the time to censoring is always observed. Okay? And when such time to censoring is always observed, they construct pack type LPBs using what's known as weighted conformal prediction inference. And they require discarding observations with small values of censoring times in the left tail of the distribution, because that messes up their inference. Okay, so that's one work on survival time that appeared somewhat recently. So this is all these are very fast-moving developments. As we were working on our paper, Sessia and Zvednik provided a method that allows for unobserved C for units with observed T, and then deal with it by basically imputing those unobserved C. Okay, and then they use weighted conformal inference, standard weighted conformal inference of Candace and colleagues. Last year, we worked, Yang was one of my former students with Arun Kuchipolta, who is a co-author for this work as well. We provided an initial approach using semiparametric efficiency theory applied to conformal prediction to deal with covariate shift problem, a standard covariate shift problem. And one can view exactly what I'm going to present here today as an extension to survival time of this approach, with all the similar benefits as the previous one. All right, so the new directions here is to generalize beyond type 1 censoring. So we will no longer assume that the censoring time is always observed. Extend methods to accumulate standard right censoring settings. Adhere to a standard double robustness criteria. So this is a little bit of a technical point. If I have some time, I'll describe what it means. And then using semi-parametric efficiency theory in the context of conformal prediction, therefore extending the Yang paper as the method does not directly apply to this current setting. Okay, let me describe the first method. Oh, yes.
When is censoring time not observed?
Sorry?
When is censoring time not observed?
When is it not observed? In virtually every study, censoring time is partially observed. The censoring time is the first time when a patient stops coming. If you haven't experienced the event. So whenever you have dropout in your study, censoring time will be observed for those patients who will censor before we observe the event of interest. For patients for whom we observe the event of interest, they no longer have the possibility of being censored because we observe the event. That's the definition.
You can't set to equal to the time of the event.
Censoring is a nuisance. We don't really, we care about, so think of mortality. I think as an example, that's the perfect example. We want to know what are the things that are causing people to die, and we want to predict when they will die based on the basis of those factors. In that context, if we don't observe the event time, that is, the person dies, that is, we lose the person in our follow-up study, the person moves or decides they no longer want to participate, that's a nuisance. So we want to get rid of it. So observing censoring is not a good thing. You want not to observe censoring. Does that make sense? Not observing censoring, that means that you, by definition, you observe all the events of interest. Because a person who is censored is a person for whom you haven't observed the event of interest. A person who is uncensored is a person for whom you've observed the event of interest. So think of censoring as a missing data problem, and you want to get rid of it. Does that make sense?
So the type 1 censoring, the issue, it's not as bad
because you observe censoring for everyone. So once you observe censoring for everyone, you have many more ways of accounting for it. It's still a nuisance, but it's a setting where, for instance, if censoring was only due to end of follow-up, and therefore, even for patients for whom you observe the outcome, you observe the censoring time as well, because you know it's the end of follow-up. Censoring is still a nuisance, but there are many more ways to account for it than if you don't observe the censoring time for everyone. Does that make sense? Because there's some symmetry between censoring and the observed outcome of interest. If I observe the censoring, I observe the outcome. If I observe the censoring, if I observe the event of interest, I don't observe censoring. But keep in mind that censoring is not a good thing. You want to get rid of it. And so, hopefully that answers your question. Okay. There are settings, and I'm not going to talk about those, where you observe an event time and you have no idea whether, initially you thought that's what you were asking. You have no idea whether that event time is a censoring time or an actual event time. I'm not going to talk about those settings. Those are really, first of all, that would be for a really poorly designed study. If you have such a study, you have bigger problems probably. So for all of these settings that I'm describing here today, censoring and event time are both partially observed. You observe the minimum of the two. And that's the standard thing that happens in trials, in cohort studies, studies where you follow people over time and then you drop out of the study. Okay. All right, good. So here are the assumptions, and these are fairly standard assumptions. For identification, we're going to need this conditional independent censoring assumption. That is, we've measured all relevant covariates such that the failure time and censoring are independent conditional of those covariates. Now, this is very similar to the covariate shift assumption. The covariate shift assumption is that conditional on your covariates, the target population outcome is exchangeable with the outcome in the training population. Okay, and so this is exactly the analog, but for censoring now. There are techniques to relax this assumption, but I'm not going to get into them today. This is fairly actually this is weaker than the usual assumption. The most standard assumption that people will assume in the literature is that C is independent of both T and X. So they will move the X jointly here with the T, and censoring would then be completely at random. Okay. Here we are basically assuming that the covariates we observe explain away the dependence between censoring and failure time. If you have residual dependence between censoring and failure time, you will not be able to use the technique that I'm going to describe today. And it's very similar to in the covariance shift problem, not being able to assume missingness at random. You have missingness not at random. So you no longer identify. If you no longer identify, you cannot build informative prediction sets. You may still be able to build prediction sets because you could get bounds, but they may not be, they may be too conservative to be useful. Okay, the second one is positivity. And essentially what it assumes is that the survival curve for both censoring, oops, there's a typo here, sorry about that. One of them should be T. I have two C's here. So both survival curves are bounded away from 0. Within levels of X. So this is similar to, this is essentially stating that for all covariate realizations X in the population, we at least observe one person, T. So this is really important because I can't get a prediction if in my training sample, I don't have any person for whom I observe the outcome for a particular value of X. So when would this not hold? For instance, if there's a systematic bias such that there is a particular covariate configuration, men age 50 to 60 who have an undergraduate degree but not a college degree, who live in San Diego. For some reason, they live forever. So you don't observe it at failure time T in your data set. You'll never be able to predict failure time because they live forever. So I'm making a joke here, but that's this is a very natural requirement. But if you don't have observed labels for people with particular covariate features, you will never be able to predict that label. Okay, so this is a positivity assumption, or sometimes it's called overlap assumption. All right. Okay, so here's the first key idea of how to deal with censoring. To deal with censoring, essentially, you will build on what's known as inverse probability of censoring weights. So we look at all the individuals with delta equals 1. What is delta equals 1? It means we observe the failure time. And among those people, we construct an L hat X such that the L hat X will be the 1 minus alpha quantile of this distribution of T given X. And the way we'll do that is we need to get rid of the censoring mechanism. And so we need to inverse probability censoring weight by the distribution of censoring evaluated at T given X. It turns out that the expectation of this statistic, so now this is a statistic, if I know the censoring distribution, I can actually estimate this quantity from data. That's an unbiased estimator for what I want to calibrate. I want to calibrate this probability, okay? And so once I have an unbiased estimator for the probability that I want to calibrate, I can now try to construct an L hat such that this probability is greater or equal to 1 minus alpha. That's known as calibration. So I'm going to pick my L hat as my prediction rule. I'm going to build my prediction rule such that this is satisfied and this quantity, the left-hand side, is greater or equal to 1 minus alpha. Does the logic make sense? I'm going to slow down here because this is the key idea. Everything else is like cherry on top of it, okay? The key idea is that once I know how to estimate my calibration probability, then I can back out how to calibrate L hats such that I have good calibration, okay? All right, as I mentioned earlier, a natural FLB will be the conditional survival quantile of the distribution of T given X. Okay, and so that's how I could construct L hat. So what we're going to do is rather than relying on Q hat T given X being a consistent estimate of the conditional quantile of T given X, we're going to find a quantile beta. This is a new parameter that we're going to introduce, such that when we estimate the probability that Q hat Tx is do I have the indicators in the right direction? Yeah, that T is greater or equal to Q hat Tx. We want to find the beta such that that quantity is always greater or equal to 1 minus alpha. If we can find such a beta, we will be well calibrated using L hat, for L hat, the conditional quantile estimate. What's interesting about this? So what's interesting is I'm no longer relying on being able to estimate the conditional quantile of t given x well. If I were relying on that, this beta would have to be 1 minus alpha. I'm saying, actually, I'm going to estimate q hat t given x, but I'm going to find the beta such that marginally the quantile is 1 minus alpha. So we're turning it on its head because we don't want to have to assume that we can do a good job estimating t given x, the law of t given x. If you do a good job, this is going to produce a very tight lower bound. If you do a poor job, it's going to contribute to a conservative lower bound, but both are going to be calibrated. And that's our goal. So this is a trade-off between constructing something that's efficient versus constructing something that's robust. And we're putting all our weights on constructing something that is robust. So beta, for this reason, because q of t given x need not be the actual quantile function, beta is what we're going to denote a pseudo quantile. All right, so what does that translate into? So it translates into this particular implementation. It's a split conformal prediction implementation. Let me just see a show of hand. Who here is familiar with conformal prediction or split conformal prediction? Is this the first time you hear about it, or you've at least seen a talk about it or worked on the topic? Okay, so I'm using if you've heard of it and you know about split conformal prediction as opposed to full conformal prediction, we're using this particular variant whereby you split the data, D, into a training set, D1, and a calibration set, D2. And then you have their respective indices, I1 and I2. You estimate the survival curves on the training set, and we use random forest or superlearner, which is an ensemble of non-parametric methods. So we're only using primarily non-parametric methods. We also have some parametric methods in there, and then we use the ensemble and find the best linear convex combination of the learners. We estimate them in D1. Then we compute the estimated coverage probability for beta on the greater values between 0 and 1. All right, and so this is the moment equation. This expression is essentially the same as, it's an empirical version of this expression, where we've now moved 1 minus alpha to the left-hand side. So we're writing it as a moment equation. Because if we do that, then we want to solve for beta equals 0, for w hat equals 0. Okay, so we want to find the beta, which makes w hat be beta as close to 0 as possible. So we want to find the largest value of beta between 0 and 1, such that w hat of beta, this quantity, is ideally equal to 0, but anything as close to 0 as possible. And we'll then use L hat being defined as q hat of t given x as the prediction rule. Okay, so a physician sees a patient with values x. They're going to take our estimate of the density of t given x, our estimate of beta hat that implies that L hat is well calibrated, and they're going to use that as a prediction rule for the lower bound. You'll get that lower bound of the prediction time. We believe that you will live at least X years with probability 1 minus alpha. It's 90%, 90%, 95%, 95%. And so you give them an idea of the uncertainty of your prediction. And the beauty of this here is that the prediction is always well calibrated. What does that mean? Out of 100 individuals for whom you produce an L hat using this algorithm, if you're calibrated at 1 minus alpha equals 95%, you're 95% guaranteed to coverage your true failure time. Okay? Let me stop there for a second. This is what the algorithm looks like. There are a number of inputs. You have to construct estimated of these survival curves. That's a machine learning exercise. There are tools to do so, and we use those tools. Okay, like yesterday, I'm going to run out of time, so I'm just going to mention a few things. Let me skip this. This is a formal theorem that gives you the coverage guarantee. Let epsilon be a number between 0 and 1 that you fix. there exists a universal constant K such that under the conditional independent censoring condition, the positivity assumption, with probability at least 1 minus epsilon over D, the probability that you cover the true failure time, conditional D, is bounded above by 1 minus alpha, that's the target, and there's a slack. The slack has two components. This component goes as 1 over square root the sample size of your training sample. So think of this as going over, converging at rate 1 over square root of n. And this converges at the rate of how well you estimate the censoring mechanism. Okay, in L2 norm. Those are the two components that you need to deal with that you will not naturally have to deal with in conformal prediction. You pay a price for censoring, and this is a price. That price is the speed with which you can estimate the censoring mechanism. This term will typically dominate this term. This is an empirical process term, 1 over square root of n. Okay. And so that's what we mean by having good asymptotic coverage. Is we're aiming for 1 minus alpha. We may not get there exactly, but in asymptotically we will get there. In finite interval, there's a slack. You will undercover or overcover by about this amount. This amount gets smaller and smaller as sample size increases. All right, so I have 10 minutes left. I do want to get into empirical data to give you a sense of how well these methods work. I'm going to mention the second part of this talk that I'm not going to be able to cover, which is AIPCW. And the main goal of AIPCW is to reduce this error term. This error term may be very slow. It's a non-punchy rate. So you'd want to reduce it. There's nothing you can do about this term. This term will always be present. And this is why it's impossible to construct, in the presence of censoring, it will be impossible to construct finite sample exact prediction intervals that are informative. Any prediction intervals that will get rid of this term will necessarily give back the whole real line. Therefore, completely uninformative prediction intervals. Okay, so let me just very quickly, I won't go into the details of it. What happens is, this is inverse probability of censoring weighting. What we'll do is we will adjust for it. And how we adjust for it is basically we realize that there's a bias. There's going to be a bias of this term that's due to S hat C given X. We're going to correct for that bias. An estimate of that bias is essentially minus this quantity. Okay? It introduces a new nuisance parameter, which is this eta, which is a regression of your conformative score. The indicator that conformity score is greater or equal to little beta, given X and being alive up to time U. And it's an integral with respect to martingale. So it's a martingale integral. I really don't have this is unfair to you guys because it's a nasty expression and I don't have time to parse it out. The main important thing is that this quantity, the second quantity, is meant to correct for the bias in the survival curve. And this shows up in the new guarantee that we get for this result, which is a bit of a nightmare to parse, but bear with me for a second. Under the same condition as the first result, we again get the coverage probability, which is this bias term. Actually, let me see, sorry, I think I have a better, here it is. Okay, so here's the new coverage guarantee of this new estimator. It has coverage 1 minus alpha up to a slack. The slack again has two terms. There's the empirical process term, it goes down as rate 1 over square root of n. And then there's this weird term, which is a combinational mini term. So let me just point out a couple of things about this to understand what's going on. It's a product, it's always a product of two bias terms. If you look at error here and error here, that's the bias of estimating eta times the bias of estimating C given X. And this kind of product bias appears everywhere, whether it's under an integral or not under an integral. The point is that you only need to focus on one of these terms to understand what's going on. The point is that you get a bias term, which is the product of how well you can estimate two nuisance functions, as opposed to a single term. If both biases are going to zero at some rate, then the product bias is always smaller than the single bias. This is known as double robustness. Okay, and so the idea is this bias term is always smaller than the bias term of inverse probability weighting, if, as we do here, you use non-parametric estimators of the nuisance function. And I apologize, it looks horrible, but it's the nature of the beast. But there is some intuition behind it, there's some structure behind it. It's basically that we want to reduce the slack as much as possible. And we use this theory to construct estimators that have small bias. All right, so in the 5 minutes left, I want to talk about some simulation studies and go back to the empirical example. So we did this in 2 settings. One where proportional hazards actually holds for both censoring and the event time, with general and exponential. And in the second one where we have, in the first one we have 2 covariates, and neither predicts censoring actually. We have censoring completely at random. The second one, there's censoring at random given the covariates. And we have more covariates, we have 4 covariates. And the underlying distribution is no longer proportional hazard, okay? And so you have to account for the censoring in the settings. And this is what it looks like. We have the new methods, IPCW or AIPCW using Cox proportional hazards model. We have the same thing using random forest, and then we have the same thing using superlearner, which is an ensemble learner. And we want these to calibrate. This is the coverage. And you can see that all of these methods calibrate pretty well. Then we have other kinds of methods that we describe in the paper, which do not have this quality of being doubly robust. And some of them perform better than others. So this is calibrated outcome regression. It fully relies on having a good estimate of the density of T given L, T given X. We have quantile regression, calibrated quantile regression. These are all variants of regression models where you rely on modeling the distribution of the survival time. And it can be quite conservative at times. Okay? So that's what this is meant to demonstrate. And this is under the first setting, the setting where things are not very complicated. There's only one covariate to contend with. Here's a more challenging setting too, where I had more than one covariate. And the point is that, again, the proposed methods actually calibrate quite well. This is not a very large sample size. Let me see what the sample size was. It was 1,000, so 2,000 in total. So this is the same order of magnitude as the application example. And the point here is that the methods seem to perform well in small samples. So here, just in closing, here is the application. So this is, again, this example where the outcome was mortality in RA population. Methotrexate was a drug that was being of interest in that population. But in addition to the methotrexate medication, we had a large number of covariates. There's a prospective cohort study of 1,200 patients. 191 individuals experienced the event prior to the end of follow-up. 1,049 individuals were censored, and they were censored during the follow-up or at the end of follow-up. It's a combination of both. And the average follow-up time was approximately a little over 2 months. Here are some of the covariates. There was a much richer set of covariates. I'm just mentioning the most common ones here. So here, because this is a real data set, we have to find a metric to evaluate the coverage. So to evaluate the coverage, we're going to use IPCW. We're going to use our methods to determine what beta hat is and get coverage with that. We'll split the data, have a held out sample where we observe the failure time. But in that failure time sample, that's held out sample, the censoring. So we account for the censoring there with inverse-probability-of-censoring weight. And here are the results. AIPCW and IPCW actually do remarkably well. Outcome regression methods tend to undercover in this application. And so we were pretty happy with these results as validation of the methodology. And you can see the lower predictive bounds are actually quite predictive. This is their distribution. Okay, and you want to make sure that you have some information in the prediction bounds and they're not giving you nonsensical results. I wanted to include this slide because this is something that people might naively do. Okay, so because you observe Y, which is the mean of TNC, if I just want a lower bound, I could construct just a lower bound for Y. That won't necessarily be a lower bound for T. Does that make sense? I just look at the time up to the event where the person is either drop out or had the event. Because I want a lower bound for having an event. That's a valid lower bound. But this can be quite conservative because imagine someone lives for 10 years, but they drop out instead after 1 month. You're telling them that they live for 1 month, right? So your bound is very large, and you could see that. You could see the range of constructing a lower bound by ignoring the fact that you have censoring and doing the naive thing. So all of this exercise is worthwhile because we shrink this distribution of y to something that's far more informative. All right, let me stop there and see if there are any questions. I think I had some slides. This is work that's been done by Rebecca Farina, Arun Kuchipota. So they're both at CMU. She's a student that Arun and I are supervising. And the paper is on the archive if anyone is interested. Any questions? What about online? If anyone is online? Yes. Okay, I guess we'll start here. Thank you so much.